Okay, this is our Unit B, topic 1.2, and this section is on acids and bases. So it starts out saying there's types of solutions. So there's 4 types of solutions that we can investigate: neutral ionic, neutral molecular, acidic, and basic. So we're going to go into what all of those things mean next. So a neutral ionic, you guys remember that ionic means it's a metal and a non-metal going together. And that's normally things that have charges. Just gonna write that on here. So these things have charges. But they're not acidic or basic. So if we were to test them with a litmus paper, it'll not change color and it'll be neutral. I don't know if you guys remember what a litmus paper is, but it's those blue and red paper that we test different acids and bases with. So this neutral ionic would not change the color. A neutral molecular, so you guys remember what a molecular compound is, or covalent. It is something that is made up of nonmetals or gases that is also not acidic or basic. So litmus paper would not change it. So those were these things, no charges. Oops. All right. And then the third type of solution is an acidic solution, and that has quite a bit of things that make it acidic. If you're looking at different solutions on figuring out if they're acidic or basic, one thing to note is that acidic things normally conduct electricity, so they have electrolytes. They're corrosive, so I always think of lemon juice as being really acidic, and that sort of like eats away at your teeth. If you hold lemon juice in your mouth, it would sort of feel funny. That's corrosive, so it sort of eats away at your skin. When we have an acid and we dip blue litmus paper in it, it'll turn red. Think of acids as being the red. They always make things turn red. They react with metals to produce hydrogen gas. So basically, if an acid goes onto a metal, it's going to make it oxidize and produce hydrogen gas. It tastes sour. So if we're tasting different things, something that tastes sour would be an acid. They can be neutralized by bases. So remembering back to what we talked about back in the day about pH scale. So remember this big long scale, 7's in the middle and 0 is over here, 14 over here. If we're looking at this section, well, these are our acids. So anything that's lower than 7 pH is going to be considered an acid, and everything higher than 7 is going to be considered a base. Okay? And then our basic solutions, they also can conduct electricity. They are corrosive as well, so just like acids, they can eat away at your skin. Something that's really we use that's corrosive every day would be soap, and some soaps are harsher than others, but soap is a basic solution, so soap can actually dry out your skin depending on what type of you use. So that is definitely an example of our everyday bases. If we were to dip them in a red litmus paper, they're going to turn blue. So acids always makes things turn red, bases turn things blue. They tend to feel slippery. So if you feel them in your hands, they're slippery. Soap is slippery, and it's a base. But also baking soda sort of has that slippery feeling if you ever feel it in your fingers. They taste really bitter if you've ever tried to eat soap or baking soda. Tastes really awful. Not sour, but bitter. These are neutralized by acids, so they bring them back towards 7. That's our neutral. And then just to refresh this, if this is 7, this is the bases. So they're on the high side of the pH scale, so greater than 7 would be considered a base. Okay? So we're going to skip this part because this is a lab, and when you guys are in class, we can do that lab. So just to refresh you on the acid naming rules, one thing we always need to remember when we are dealing with an acid is that an acid always starts with a hydrogen. So I'm going to write that. I always say at the first. There's like one exception to that, acetic acid, but almost all acids start with a hydrogen. And then the rules that we have. So I'm going to write these rules down and then we can do some examples. Oops. Yeah, this is going to be difficult. So the different rules we have IDE, ITE, and ATE. So if something has an "ide" ending, it's a hydroic acid. It's not the best pen. And then if it's an "ite," it's a something us acid. And then an "ate" ending is an ic acid. Okay. So right at the top here, I'm going to do an example of that just to show you. So if we had, maybe I'll do it at the bottom. If we had a HNO3, our first job here to name this would be saying, oh, well, it has a hydrogen at the first of it, therefore it's an acid. So we know right away, H at the first, it's an acid. So then we can go to these naming rules, okay? So our next job is to look at this part. We're only concerned about the NO3. And we can go to our periodic table that has a little chart of polyatomic ions on it. That big one that I had laminated for you. And that one will tell you what NO3 is if you don't remember. But if we look that up, NO3 is nitrate. Okay. So now that we know that that's nitrate, we can look at the ending of the word ate. All right. So that brings us back to our acid naming rules, which we see 8 right here. 8 would be a something ic acid. So all we do here is we take off the 8 and then we add ic acid. So that ends up being nitric acid. Okay, so you're just putting the ending of the polyatomic ion, finding which one it corresponds to in the acid naming rules, then drop that ending and plug it into the space. And this one I have a really bad writing with, but that is how you would do that. All right, so that's a refresher on how we would name acids. All right, so this is going into some new things. So Arrhenius and acids. It says Arrhenius said, so this was a guy, chemist back in the day. He said that acids form aqueous solutions that contain hydrogen ions and a negatively charged ion. All right, so he said basically if we were to put an acid in water, we would get, it would break into its ions. Let's use the one we just did, which is HNO3. It's a really bad 3. If we put that in water, so by putting it in water, you just write AQ, draw an arrow. So HNO3 in water would change into H plus and NO3, -1. Okay? So that's all he was saying there. He was just saying that if we were to mix it with water, it's going to break into its ions. And if we look back at what it said as an acid, it said that they have electrolytes, or they conduct electricity. Well, remember, we need ions to conduct electricity, so it makes a lot of sense that we can conduct electricity because these ions are breaking up that molecule into their ions. All right, so that's all that means. So he was just saying that was sort of his theory. And then again, he said the exact same thing for bases, except for if we put them into an aqueous solution, they will contain OH ions and a positively charged ion. So if we go an example here, I'll do sodium hydroxide, because that is a base in water, breaks down into Na plus and OH negative. All right, so that is all he was saying, is that when we put stuff in water, it's going to break down into its ions. And then neutral substances, he said that solutions that do not have a hydrogen or hydroxide ion are called neutral. So I'll give the classic example. Let's do NaCl. If we were to put that in water, that's sodium chloride or salt. It would give you Na with a positive charge and Cl with a negative charge. Still an ionic neutral solution, but no OHs or Hs, which means it's not an acid or base. Right. So that brings us to our first practice problems for topic 1.2. So I'll stop there and upload this for you, and then I will continue on to the next part later.